All right, so in this module we're going to talk about the defect reactions and how we write them for stoichiometric defects. So we talked about some of these before, right? These are the ones, as the name implies, that maintain the stoichiometry of the crystal. So not all defects that we have to do this, and we'll talk about those in another section, but these do maintain the stoichiometry of the crystal. And we've actually already talked about these before. We're just going to look at the defect reactions of them. So we've already seen the Schottky, we've already talked about Frankel, and we've already talked about misplaced atoms. So those are some examples where we don't affect the stoichiometry. And so let's start with Schottky. So again, these are the charge equivalent number of vacancies on each sublattice, or on each sublattice. So let's look at it in the generic case of an MO oxide. Okay, so now we're going to start to get into how we actually write these reactions. So with every reaction, we have a reactants and products, right? Well, in defect reactions, our reactants are always, fairly straightforward, right? We're usually talking about a perfect crystal. So we're usually referencing a perfect crystal. And so in a lot of cases, what we do is we either write null, or we could just write perfect crystal. So this just kind of represents what is on the left side. So I don't get too picky when I go over, your results for these, but just something to indicate a perfect crystal. The other way that you could write it, and I just want to show you that for clarity, is if you want to say something's a perfect crystal, you basically want to illustrate that everything is in its correct spot and there's nothing extra. So this, since this is MO oxide, what we could also say is M is in the M sites and there's no change in the charge, plus O is in the O sites and there's no change in charge, right? So, but this isn't required unless you just want to show that. So let's go ahead and write it. So the perfect crystal then goes to, and so you just write this like a normal chemical reaction, and then we write our defects. And we've already talked about the Kroger-Vink notation in quite detail, but now we're going to start pairing them, and we need to look at the mass balance, the charge balance, and the ratio of regular sites. So we're going to do that in this example. So if we're talking about an charge equivalent number of vacancies on each sublattice, we're going to have a vacancy of M, and we're going to have a vacancy of O. So let's go ahead. We know there's going to be a vacancy of M. The charge on this is going to be 2 plus, since the charge on oxygen is 2 minus. So if we remove a plus 2 charge, that's going to be a minus 2. So we're going to have a minus 2, so 2 dashes. Plus, we're going to have an oxygen vacancy. And we've already actually gone over this in a previous module, that's double dot. All right, so that's the first step. We've wrote the species that we're going to have. And in this case, that charge equivalent number is 1 to 1, right? That's what we've seen before. We pair 1 with 1 since the stoichiometry is 1 to 1. So we need one formula unit. And just to be clear about that, we can check it over with the charge, right? So this is a quick way, obviously, that we can check that. So we have minus 2 charge, plus 2 charge, and so that's charge balance, because the perfect crystal would be uncharged, and then this is going to be uncharged. So that's the first thing that we want to look at. All right, so let's just go through those and kind of check these 3 rules that we're talking about. So for mass, so a perfect MO crystal would have essentially the mass of this. We would have one metal and one oxygen in terms of a mass. So when we write it like this, and we only talk about the vacancies, right? We're not talking about what happened to the metal here and the oxygen, because we're only showing vacancies. So technically, if you want the mass to be balanced, you would also have to write M goes to an M site. So this would basically imply that you're removing that metal and it's going to the surface or somewhere. And so it goes to another site and there's no change in charge there. And also, the same thing would have to happen with oxygen. So technically, you have to write these if you want the mass to be balanced, but I will tell you now that you never really see these except in examples. So people don't typically write this to consider mass balance, because it's implied that those metal and oxygen ions have to go somewhere. So that's just, again, to be technically balanced, we would also have to discuss where those metal and oxygens go. Charge-wise, we've already balanced the charge, right? So -2, +2, these are no charge. So we've got that balanced, but you want to check that each time. And if it's not balanced, then you obviously would have to either reconsider the reaction or balance the coefficients out front. So here it's 1 and 1, but for something else it could be different. So we've already balanced that. So let's go to the last one, site. So that site ratio. And again, it's A over B equals M and M plus the vacancies, and X over X plus vacancies of X. And so here, we want to look at this ratio. And so we know that this should be 1, right, based on our coefficients for this. So this should be 1. But what we want to check is that these do equal that. And so here we have 1 metal vacancy, and then the extra one that we added to compensate for where that metal goes. So if we hadn't written that, again, you see here a problem. So this is 1 plus 1. And then the same thing with the X, or oxygens. You have 1 vacancy, but we've compensated it for with an extra site. So we've created 2 new sites, but we've balanced those 2. And so we have 1 over 1, and so that still equals 1. So everything is balanced there. But you can see that if you hadn't written this out, that the balance wouldn't have been, we wouldn't have had these to know specifically. We still would have maintained the same ratio, but it still would work out. But it's nice to put this just for formal clarity if you have to go through all of these steps.